Hi, welcome to a discussion of what we know right now about first and second derivatives. So this is a little bit tough for students a lot of times because you're going through all of the mechanics of finding derivatives and the limit definition of derivatives, and all of a sudden we start to use derivatives, right? And then before long you become comfortable with the use of a derivative, and all of a sudden we introduce the second derivative, right? The derivative of the derivative. And keeping in mind or keeping track of what all these things do and what they can tell us can be very, very tricky for people. So what I'd like to do today is take a little bit more time to discuss the first and the second derivative and the function itself, and talk about what each one of them sort of does for us. So let's kind of think about this, and sort of lay out the three major players in our game. We've got f of x, we've got f prime of x, and we've got f double prime of x. Now each one of these is a function, so each one of them has a graph. Each one of them takes an input and gives us an output. Let's be kind of clear about them, right? The second derivative is the first derivative of the first derivative, with all the rules that go along with that. But let's talk about what we really care about with functions. With functions, we typically like to think about two things: whether their outputs are positive or negative, and whether their outputs are increasing or decreasing. All right? One of those is geometric, increasing and decreasing. We can kind of picture it. One is very algebraic. Hey, I put a value of x in, I get some output out. So let's talk about that. All right? Scroll up a little bit here. Now, oftentimes what we do is we just want to think about what we can say in terms of positives and negatives increasing and decreasing. So let's talk about this. Let's start with f prime. Let's say f prime is positive. What does that really tell us about the other two sort of players in the game? Well, hopefully you know that it tells you that f of x is increasing. But the thing is, a function's graph can increase in two distinctly different ways. It can either increase like this, or it can increase like this. In one case, the graph is concave down, and the second derivative is negative, right? And in one case, the graph is concave up, and the second derivative is positive. Sorry about that little positive symbol up there. Right? We can do the same thing for negatives. Negative f primes, that is. If f prime is negative, then I know f of x is decreasing, but yet again it can decrease in two distinctly different ways, like that and like that. So if it decreases like that, well, then we know that f double prime of x, right, is positive because the graph is concave up. And if it decreases like this, then f double prime of x is negative. All right. So if all we know is whether or not the first derivative is positive or negative, then all that can tell us is whether or not the function is increasing or decreasing. We don't know whether the function is negative or positive itself, right? We can easily, let's say, have a function that is increasing and only has positive values. So we can have a function that's increasing and only has negative values, right? The positive-negative nature of this guy really tells us nothing except for where it is compared to the x-axis, where it, being the function, is. So let's talk a little bit about the second derivative and what it tells us. I'm going to just kind of scroll this out of the way for a minute. I'm going to rewrite down our three players in the game. F of x, f prime of x, and f double prime of x. All right, and the real key is always remembering that f double prime of x came from taking the derivative of the derivative. That's actually where the double prime notation comes from, right? I've got a function and I'm taking its derivative, but that means it's been taken twice. So now let's talk about whether this is positive or negative. Now, everything that f prime told us about f f double prime should tell us about f prime. So if f double prime is positive, really, at its essence, what that tells us is that f prime of x is increasing. And if f double prime is negative, then f prime of x must be decreasing. All right, but then what does that mean about the graph of f of x? All right, so if the graph of f prime is increasing, then that means that the slopes are increasing. But slopes can increase in two ways. One way is pretty obvious. Oh, that slope is increasing. Going from, a slope of, let's say, positive 1 to a slope, let's say, of positive 5. But slopes can increase in a much more subtle way. You see, slopes are also increasing along this curve because they are becoming less negative. Maybe that's a slope of negative 5, and that's a slope. That was supposed to be a slope of negative 1. So if the slopes are increasing, then what we really know is that f of x is concave up. That's one acceptable way of defining concavity. It's just saying, look, a graph is concave up at any portion along it at which the slopes are increasing. But for the slopes to be increasing, the derivative of the slope function must be positive. We can make exactly the same argument about f double prime being negative. If f double prime is negative, it means that f prime is decreasing. The slopes are going down in numerical order. And again, that can happen in one of two ways. We can either have the way that makes all the sense in the world, right, which is this. Everybody would agree that the slopes are going down on that curve, even if it's discontinuous, because this is a less steep portion. Again, let's just arbitrarily assign some slope values. Let's say that's a slope of 5. Maybe that's a slope of 1, right? Those slopes are decreasing. But again, more subtly is the situation here, where we have slopes decreasing, but the curve is actually getting steeper. Maybe that's a slope of negative 1. Maybe that's a slope of negative 5. But the slopes are still going down, and therefore we are concave down. All right. So it's quite interesting, right? Putting all of this information together, we get all sorts of different things, right? We have our ability to find inflection points, turning points, justify whether a turning point is an inflection point or not, right? Just think about that major use of f prime of x, right? F prime of x's major use is to tell whether f of x is increasing or decreasing. That's why when we have f prime, right, we say something like f prime of x is equal to, let's say, x minus 2 squared. I'm just making something up. X minus 5, say x plus 1. Well, we know that we have horizontal tangent lines. We know the slope is 0 at, that was an interestingly unstraight number line. We know that the slope is 0 at x equals negative 1, at x equals 2, and at x equals 5. But when we actually do a sign analysis, what we find is a positive first derivative there, so our function is increasing, a positive first derivative there, so our function is also increasing. I'm sorry, my mistake. I just did that in my head a little bit too quickly. Yeah, thank you, eraser, for working. Go back to my pen. We would find a negative first derivative there, decreasing, but also be negative there, decreasing, and positive there, increasing. So because we can use f prime's outputs to tell us whether f of x is increasing or decreasing, we can easily tell what this graph has in terms of local minimums and local maximums, right? We can easily just look at it and say, well, since the function itself went from increasing to decreasing at negative 1, and I know that because the first derivative changed from positive to negative, I can easily tell that I have a relative max here. And of course, we have that standard wording for justifying it. And likewise, because the first derivative goes from negative to positive, we know that the function goes from decreasing to increasing, so we know we have a relative or a local minimum. Right? The remarkable thing is, it doesn't tell you really anything about concavity. Right? In order to know about concavity, you really need to know whether or not the first derivative is increasing or decreasing. Right? And then that gets us back into the discussion from up here and what the second derivative tells you. Let me clear out some space. See if I can delete some of this. Some room to work. So ultimately, right, the second derivative does tell us whether the first derivative is increasing or decreasing. But then that gets at the concavity of the curve. And that line of reasoning is something that you definitely want to feel comfortable with at this point. You want to be able to say, all right, I know if f double prime of x, if it's output, right, that's what I mean by this. When I say f double prime of x is greater than or equal to 0, then we know that f prime of x would be increasing, which tells us that f of x is concave up. I wouldn't know whether it was concave up like this or whether it was concave up like that. I wouldn't know that, because to know whether it's this or this, think about this, I would need to know the sign of f prime. Right? F prime here would be negative, f prime here would be positive, because the function itself is decreasing versus the function increasing. We can have exactly the same type of reasoning for f double prime. Just going to pause the video for a moment. So we can have exactly the same type of reasoning for a negative second derivative if f double prime of x is less than 0. Right? We automatically want to be able to string this kind of reasoning along. Then f prime of x is decreasing, which means that f of x is concave down. Again, keeping in mind that concave down can come in two forms, one where the first derivative is positive and one where the first derivative is negative. So, at this point we can use that information about concavity to do something that's kind of cool. And this is the last thing I'm going to talk about. This thing called the second derivative test for local maximums and local minimums. And it's really quite neat, right? Just delete this really quick. So, I might as well get rid of all this mess too. Myself a nice clean board to work on. Alright, so the second derivative test for local maxes and local mins is awfully neat. Because what it says is that we can actually, if you will, avoid writing out a first derivative number line test to figure out where local maxes and local mins are. You know, we don't actually need this if we know information about concavity. Alright, now you might say, yeah, but I always like this. Well, it's good to have various approaches to doing things, and there are some types of problems, some ways problems can be constructed, where it would actually be quite difficult to use a first derivative number line test. Alright? But the classic issue is, you know, if we have a point, you know, let's say x equals a, where we know the first derivative is equal to 0. In other words, we sort of have a candidate for a turning point. Maybe a turning point, may not, but we don't know whether it's a max or min. If we then know the sign of the second derivative, like let's say that the second derivative was negative. Well, what would we know? We'd know that the function was having a plateau, right? That's due to the first derivative being 0. And we'd know that the graph was also concave down there, so the tangent line would need to lie above it. So what we would know is that we would have a relative maximum. Alright? On the other hand, if the second derivative was a positive number, that would tell us that we would have this, plateau due to the first derivative being 0, but that we would be concave up. So we would have a relative min. Alright, a kind of a neat way of forcing students to know this would be to have a problem such as the following. Let's say I knew that f prime of 5 was equal to 0 and f double prime of x was equal to, I don't know, say I had 2x times x minus 7, right? And I wanted to know whether x equals 5 was the location. Is x equals 5 the location of a min, or max? See, it's going to be pretty hard in this case to set up a number line for f prime for a very obvious reason. We don't know what its formula is. We don't have its formula. On the other hand, if I simply take f double prime and I evaluate it at 5, I can know whether the graph of f of x is concave up or concave down at 5. Well, let's see how that looks. We have 2 times 5 times 5 minus 7. That's 10 times negative 2, and that's negative 20. So what I know is I know that f of x is concave down. Now all you have to do at that point, is picture a concave down parabola. That's all you have to do. Don't make it fancy, don't make it tough. Say second derivative's negative, gotta be looking something like this, right? And therefore x equals 5 is the location of a max. Alright? So I'm going to stop there. I didn't discuss how to find inflection points, but I think that's pretty straightforward. By definition, inflection points are places where the second derivative changes sign, so you do a sign analysis of the second derivative. I also didn't talk about particularly finding turning points using first derivatives, except for that little bit of a number line talk. So I hope that this has helped. I hope that it's given you a little bit of extra instruction, a little bit more thinking and discussion about how it all works. Go back and watch the other videos that have been recorded for the class. I'll see you soon. Take care, and do good thinking.